right, so for our first example, how do I integrate cosine pi x? It turns out to be 1 over pi we get from our u substitution. Sine of pi x. No dx, right? No dx. Evaluated between 0 and 1/2. Alright, make him stop. Alright, 1 over pi times sine of pi half minus sine of 0. And we get our 1 over pi, and what are the units? Meters, also known as joules. Alright, easy enough. So now let's look at a classic problem. There we go. The cone problem, the conical tank. And on this one, you should put stars around it. You should do whatever you want to do to highlight it. This is a work problem that shows up in some form all the time. Okay? So, it says the conical tank in the figure is filled to within 2 feet of the top with olive oil, weighing 57 pounds per feet cubed. Alright, so right there, they're saying it weighs 57 pounds per foot cubed. Well, the unit of force is pound. So this is not our unit of force quite yet. We need to think about how we will make this, or how we will use this to get to our unit of force. And then it says, how much work does it take to pump the oil to the rim of the tank? So let's be clear. We have this tank, it's filled up to 8, from the bottom up to 8. And when they say pump the oil to the rim of the tank, they mean pump all of the oil. Right? So we are emptying the tank. It's spilling out of the top. All right. So we are going to find work. And that is the integral of force. In this case, it'll be a y. Times our displacement. And we're going to be a little more clear about this, but this is displacement. And it's going to have some different definition than dy. All right. So to find our force, the unit of force is pounds, so I need to multiply this 57 by what? Volume. All right, and as with everything in calculus, we take a tiny little slice. We have our cylinder, and the height of the cylinder is dy, and the volume of that little slice is going to be pi r squared dy. And what is r going to be? 1/2 y. The distance from here to here, which is out to our function, 1/2 y squared dy. So the dy in this problem is actually the height of our little slab. It is not the displacement that we're going to find here. We need something else to talk about the displacement. So, if I want to consider this one slab, it happens to be right now y units up from the bottom. So what is the displacement to move that slab up to the top of the tank? 2 if we're at 8, right? 10 minus whatever y we're at. So if I had one down here, right, it's going to be 10 minus whatever that y value is. How far I'm going to have to move that to get it to the top. So that's the displacement that usually we would see as dy. So our work ends up being 57 times pi force y squared and the dy is part of that, to get our volume of the cylinder, times how far I have to move that thing, which is 10 minus y. Now, when we think about where we're going to integrate this over, what interval we will integrate over, you have to think about where the slabs are. So the slabs will go from 0 up to what? Not to 10, to 8, right? The oil starts off only at from 0 up to 8. So our integral then is going from 0 to 8. And that is the integral that we would solve. Could we do that one by hand? Yep, not too bad. We would have 57 pi fourths out in front of the integral, and we would distribute y squared through, and it's the power rule one, so that one's pretty easy. All right, questions on where our integral comes from? Okay, the common error spots on this type of problem are the limits of integration and making sure that you get the force correct. Okay?
Why did we do the 8 and not do the 10?
Because you need to think about the slabs that we're moving. And the slabs that we are moving are only existing right now from 0 up to 8. And then the 10 minus y takes care of how far we have to move each slab. Okay? All right.
I'm a little confused about where the 10 minus y is coming from.
Okay, so...
The formula is like force dy.
Right, generally it is force dy, but this dy is how far we're moving it. So if I have a constant force, then work is force times displacement, how far I move it. Okay? So in this one, when I had to get my force to figure out, I found the force needed to move just one slab, which includes a differential, which is dy. And how far I have to move it this time is actually the 10 minus y. That's the displacement. This dy is part of our force. So we have force times displacement for this problem. Okay, and our differential ends up coming in our calculations of the force. All right, let's take a look at the other type of problem that I want to consider. I'm not really going to take the time to look at fluid force and fluid pressure. They're interesting, but they don't come up quite as often. A very useful application of integrals is in probability and statistics. So, the first thing that we need to understand is the definition of a probability density function. You'll see it abbreviated PDF. And a PDF is a function with the domain in all reals, and the function is above 0 everywhere, so it's never going below the x-axis. And the area under the curve from negative infinity to infinity of the function is 1. So what is the probability of something that is certainly going to happen? It is 100%, or a probability of 1. So if you are integrating over a probability density function, then it makes sense that if I integrate over the entire function and find the total area under the curve, what you're finding is the probability of a certainty. And that's why it's equal to 1. Okay, and a very common PDF is the normal probability density function. So let's review a little bit the idea of a normal distribution. Let me make this a little bigger. All right. So this is an example of a normal probability density function. And we have a normal distribution where the center line is what? 0, but what is it with respect to the data? The mean, right? That center line coming down is the mean. And then the standard deviations measure how our data is scattered about the mean. All right? And if it falls into a normal distribution like this shape, the bell curve, then 68% of our data falls between or within 1 standard deviation of the mean. 95% falls within 2 standard deviations. And what do we have? 99.7% falls within 3 standard deviations of the mean. It's just the way the data falls out if it is a normal distribution. Okay? And we can use this probability density function to help us predict the probability of certain events occurring. All right, so the function that makes this bell curve is given here, and this you need to get into your notes. This is the normal probability density function, also called the Gaussian curve, and it is always in this form of the function. F of x is 1 over sigma, that's the standard deviation, times root 2 pi, times e to the negative x minus mu, mu is the mean, squared, divided by 2 sigma squared. I can get that in front. Oh, sorry. There we go. So you want to have this available for our next example. Mu is the mean, and sigma is the standard deviation. So if I plug into this function for a set of data, I'm going to get my bell curve, and it's going to be situated where the mean is the center line, and we can calculate our standard deviations out. Okay? Make sure you see this is division. Kind of hard to see that line. I would not ask you to memorize this function. Okay? If I ask you to work with it, I will give you the normal distribution function. All right, so let's see what we can do with this example. Do we have it down? You'll see sometimes going. Okay. All right. So that's just a summary of how the data is distributed with a normal distribution. Okay, the weight of spinach boxes. Suppose that frozen spinach boxes marked as 10 ounces of spinach have a mean weight of 10.3 and a standard deviation of 0.2. This is a normally distributed set of data, so I know I am dealing with a bell curve. Draw it nicely. Where this center line is what? 10.3, and the standard deviations are 0.2. So that would be 10.5 and 10.1. And 2 standard deviations out would be 9.9 and 10.7. And then 3 would be 10.9 and 9.7. Now, from what we saw about the data under a normal distribution, 99.7% of our data falls within those two. So generally, you don't really have to go far beyond that. Okay, 3 standard deviations usually gives you enough information for most problems. All right, so let's see what we can do. What percentage of all such spinach boxes can be expected to weigh between 10 and 11 ounces? Well, if this is a normal distribution function or a normal probability density function, our f of x for this problem will be 1 over what? 0.2 square root of 2 pi times e to the negative x minus 10.3, is that squared? Squared over 0.08, which is what? 2 times 0.2 squared. Okay, just so we can see where we're plugging everything in. All right, so there's our function, and we'll just refer to that as f of x for our problems now. And if I want to know the percentage of all spinach boxes that falls between 10 and 11, all I need to do now is my area between the curve from 10 to 11. So that is the integral from 10 to 11 of f of x dx. And this you would do in your calculator. Just be careful plugging in all those answers. Okay? And part B, says, what percentage would we expect to weigh less than 10 ounces? What do I do for that one? 0 to 10. Now, in the book, they remind you that we have 99% of the data falling between 9.7 and up, right? So they said you don't really need to go to 0. You would probably get enough information by going from 9 to 10. Because that is 5, 3, 1, 4 more standard deviations out. Okay, so we've got, if we went from 9 to 10, we would probably be within 7 decimal places of the exact answer. Okay, so we'd be have a very, very good approximation. Don't know why it's going so circle. All right, so now finally, what is the probability that a box weighs exactly 10 ounces? What's that interval? 10 to 10? And what will that equal? 0. And let's see if that makes sense to us. How many possible weights are there in our distribution? An infinite number, yes? So the probability of getting exactly 1 weight using this model would be 1 out of a gigantic number. It's be extremely close to 0. So it makes sense using this model. All right. So now, what time are we at? 10:17. Okay, so everyone is clear on your homework. It is a change on the assignment sheet. Nick, did you get it?
Yeah.
Good. 1, 3, 17, and 30 from section 8.5, and you start your chapter review and you make your study guide over the weekend. Okay? That's all I have.